Class 11th Chemistry, Unit 5, States of Matter, and in this video we will discuss about kinetic molecular theory of gases and deviation from ideal gas behavior. First come to kinetic molecular theory of gases. A theory is a model, that is a mental picture that enables us to better understand our observations. We have discussed the various gas laws, Boyle's law, Charles' law, Gay-Lussac's law. Okay, all these laws are based on the experimental observations. Now, what is the theory behind these observations? Why gases follow or obey these laws? Okay, the theory that attempts to elucidate means explain, the behavior of gases is known as kinetic molecular theory. It provides a microscopic model of gases. Now, assumptions or postulates of the kinetic molecular theory of gases. First one, the actual volume of the molecules is negligible in comparison to the empty space between them. The gas particles, that is atoms or molecules, are considered as point masses. This assumption explains the great compressibility of gases. Actually, when we compress the gas, whatever the empty space between molecule, that empty space is reduced. Okay. Second one, there is no force of attraction between the particles of a gas at ordinary temperature and pressure. Okay, no force of attraction. But as we know, gases expand and occupy all the space available to them. This postulate explains this tendency of gases. There is no force of attraction. That's why gases expand and occupy all the space available to them. Particles of a gas are always in constant and random motion. A gas does not have a fixed shape. This is explained by this assumption. If there is no random motion, then gas molecule will have fixed shape. But as we know, gas does not have a fixed shape. Next one, particles of a gas move in all possible directions in straight lines. During their random motion, they collide with each other and with the walls of the container. And in this way, pressure is exerted by the gas. Next one, collisions of gas molecules are perfectly elastic. Now, what is the meaning of this perfectly elastic? It means total energy of molecules before and after the collision remains same. If there were loss of kinetic energy, the motion of molecules will stop and gases will settle down. Okay. At any particular time, different particles in a gas have different speeds and hence different kinetic energies. Every particle has different speed and different kinetic energy. Although the individual speeds are changing, the distribution of speeds remain constant at a particular temperature. In kinetic theory, it is assumed that average kinetic energy of the gas molecule is directly proportional to the absolute temperature. These are the postulates of kinetic molecular theory of gases. Now, behavior of real gases. Deviation from ideal gas behavior. We already discussed what is the meaning of this ideal gas. Ideal gas, the gas which follow the gas laws at all conditions of temperature and pressure. At constant temperature, PV versus P plot for real gases is not a straight line. Just you see this plot of PV versus P for real gas and ideal gas at 273 Kelvin. This y-axis PV is taken and on x-axis P is taken. For ideal gas, you can see this is a straight line. or we can say this is parallel to this x-axis. Okay, and for real gases, we can see two type of curves for real gases. For hydrogen, for dihydrogen, that is H2 and helium, as the pressure increases, the value of PV also increases. You can see this is hydrogen and this is helium. For carbon monoxide and methane, first there is a negative deviation from ideal behavior. The curve then crosses the line for ideal gas and after that shows positive deviation. Now you can see for this CH4 methane, first of all this is decreases, then crosses this ideal line and then it is increases. In the same way for this carbon monoxide, first there is a decrease, then crosses this ideal line and then increases. It means at all the conditions of pressure, these real gases will not show the ideal behavior. Real gases do not follow ideal gas equation perfectly under all conditions. Now again, if we plot, that is between P and V, plot of pressure versus volume for real gas and ideal gas. This is pressure, this is volume, and this red line represent for ideal gas and this is blue line represent for real gas. Now, at very high pressure, the measured volume is more than the calculated volume. At very high pressure, that is this. At this condition, if you compare, this is the volume for ideal gas. Okay, and this is the volume for real gas. So we can say that is at very high pressure, the measured volume is more than the calculated volume. Okay. At low pressure, measured and calculated volumes approach each other like this. As the pressure decreases, this is lower pressure, and then these two lines coincide for some time, for some place. It is found that real gases do not follow Boyle's law, Charles' law, and Avogadro law perfectly under all conditions. Now, two questions arise. Why do gases deviate from the ideal behavior? And second one is, what are the conditions under which gases deviate from ideality? We will try to find out the answer of first question. Why do gases deviate from the ideal behavior? And to find out the answer of this question, we will once again recheck the assumptions of kinetic theory. In that case, two assumptions of the kinetic theory do not hold good. These are, there is no force of attraction between the molecules of a gas. And second one is, volume of the molecules of a gas is negligibly small in comparison to the space occupied by the gas. These two postulates of kinetic molecular theory do not hold good. If assumption A is correct, the gas will never liquefy, and as we know, if we apply the pressure and cool the gas can be liquefied. Okay, and liquefied means there is some force of attraction between the molecules of gas. And if assumption B is correct, the pressure versus volume graph just we have discussed of experimental data, that is real gas, and the theoretically calculated from Boyle's law should coincide. Okay, that's why this B, we can say that is the second postulate or second assumption is not hold good. Now second, what are the conditions under which gases deviate from ideality? At low temperature and high pressure, real gases show deviation from ideal gas laws because molecules interact with each other and intermolecular forces become significant at low temperature. And at high pressures, molecules of gases are very close to each other and actual volume of gas particles is also significant. Now let us see. This is the gas at low pressure. Okay, and when we apply the pressure, when we increase the pressure, now just see, the empty space between these molecules is reduced and we will get this one. Okay, that's why molecules come close to each other at high pressure, and when they come too close, some intermolecular forces are significant among them. You can also see, if pressure is low, then volume of gas is negligible. Actually, volume of we are having the two things: volume of gas particle and volume occupied by gas. Is it clear? Volume of gas particle and volume occupied by gas. This in this diagram, first see this, we can say if this is a gas particle. Okay, we can say this is the volume of this one gas particle, this is the volume of this gas particle, and this one in which this gas is enclosed, this is the volume occupied by gas. Is it clear? Now you can see, if low pressure is there, this volume occupied by gas is very high. That's why this is the volume of actual volume of the gas particle can be ignored. This is negligible compared to this volume occupied by the gas. But when we apply the pressure, what will happen? What will happen? The empty space between the gas particle is reduced, but there is no change in the volume, actual volume of the gas particle. Now you can see this. This is the actual volume. This one and this one, there is no change, but the empty space between the gas molecule is reduced very much at high pressure. Okay, that's why at the high pressure the actual volume of gas particle is not negligible compared to the space occupied by gas. Is it clear or not? Thank you.